Adding now the constant basic state, we remember the equations we looked at obviously has Doppler and non-Doppler terms. Obviously that means the wave number and frequency affected by the basic state and terms that affect the dynamic balance. Right? We looked at that in chapter 5 that you can revise for yourself. Going back to this form of equation with this complication expressions of P and Q, the linearized form of the equation was written in terms of meridional structure functions, d squared v dy squared plus gamma squared y v equals 0. If you remember, this is the refractive index, basically relates to the turning latitudes where waves then become decaying exponential solutions, also related to the potential well width of the equatorial trapping. So all these things begin to relate to each other. So in this case we had written the meridional perturbation velocity as some Vy times exponential of minus 1/2 Py dy, where Py is the coefficient of this equation that we had looked at in the last podcast. The equation d squared v dy squared plus gamma squared y v equals 0 is again the harmonic oscillator and becomes different when there is no basic state, just becomes a Laplacian. Gamma squared y is the refractive index, which is this complicated looking thing. It's a square of the refractive index, and u equals u bar y we are dealing with on an equatorial beta plane. We already looked at the error we make with this assumption as we go further off, but there are many details involved there that we are not going to look at. So again, this complicated looking thing has non-Doppler terms and Doppler terms as before, where the Doppler shifted frequency is now written in terms of this structure function with the wave number of the ith mode, and the intrinsic frequency is can be written here, of course, by moving this to the other side and this in terms of the basic state and the wave number. So here the Doppler frequency, Doppler shifted frequency is a function of k, as we know. Neglecting these terms here, which are small compared to the other terms, so we are neglecting this one and this one, which simplifies the equation d squared v dy squared plus this complicated looking thing, which obviously is a third order equation because there is a square here and 1 over omega d here. So if you multiply it through, you get a cubic, which means you get 3 solutions, which we will look at. We talked about 3 families of waves, so there we are. This again can be written as a minus b squared y squared equal to 0, which is what we had for the basic state being stationary. So the equations now look very similar. In this case, the solutions are going to be quite complicated. Remembering A is this one, B is this one, Vy is now can be written, this equation has a general form solution in terms of Hermite polynomials. So Vy is then Hermite polynomial of order n, b to the 1/2 y exponential minus by squared over 2. So there is the latitudinal dependence of the waveform, turning latitude, exponentially decaying solutions, etc., because you don't want a solution that grows with latitude and so on. So some choices have been made. Hermite polynomial is the nth order function written this way. Again, complicated looking thing, and it's y in this case is our complicated thing here. The main thing to remember, obviously we're not going to remember all the expansions, but the odd Hermite polynomials are anti-symmetric about the equator, and the even numbers 0, 2, 4, etc. are symmetric about the equator. So that gives you a sense of where we are headed in terms of the solution. So you can write meridional derivatives of the Hermite polynomial this way, and the relation between the n plus 1th term with the nth and n minus 1th term in this way. All these help us later on with the modes. Okay. Deriving a general dispersion relation for a constant basic state then can proceed. Vy is this expression again, that we are getting a solution for this form where a is now with the Hermite polynomial 2n plus 1 or times b, right? So b is that complicated thing that I'm not going to go back to probably. Then the general dispersion relation for nth mode of the wave is a function of the Doppler shifted frequency, gravity wave speed, zonal wave number, beta, and then this expression of the background state. Okay, this is where again you remember this is related to the Raspy radius of deformation. So we define an equatorial Raspy radius of deformation. We had defined before for shallow barotropic fluid of depth h the Raspy radius as c over f, essentially how far a gravity wave can travel in one inertial period. So gravity wave speed is square root gh divided by f, the Coriolis. In a baroclinic fluid, that is related to the Brent-Vesala frequency. So Raspy radius of deformation, which is still c over f, is written as ng over f, right? The Brent-Vesala frequency and the scale height g. Okay. The turning latitude then becomes a function of the background state. This is critical. So we'll see that the easterly state tends to reduce the turning latitudes and makes the waves more equatorially trapped, whereas for me this should be westerly, this should be easterly. You do it for yourself. A westerly flow regime tends to expand the trapping distance or the turning latitudes, so you can see those dependence, and you can see why the basic state can affect the beta influence on the turning latitude. So they are related in the sense the restoring effect of the Coriolis in terms of beta can be altered by the basic state. Okay, so try to get a physical sense of these things. The physics is important, so I'm sure as we look at more real dynamics of the atmosphere and ocean, it'll become clearer, but we are actually saying very few things. Which way the waves move, phase speed, group velocity, dispersive, non-dispersive, and meridional structures, which means turning latitude and equatorial trapping. So now we can write the meridional velocity in terms of the Hermite polynomial and the basic state. Write this as a meridional structure function where f and y is exponential of minus 1/2. So we are simplifying this with the Hermite polynomial into this beastly looking thing where we have now the equatorial Raspy radius. We will see that equatorial Raspy radius of deformation is important for Raspy waves and their characteristics, but when it comes to forcing to generate the waves, it is still the Raspy radius related to c over f that is critical in terms of which produces waves large enough to feel the rotational effect and which forcing is small enough that gravity waves can just dissipate away without feeling the rotational effect. The equatorial Raspy radius then has this expression b to the minus 1/2. B is of course c over beta, so we can write this expression. So c over beta 1/2 times 1 plus k u bar over omega d minus 1/4. So you can now see the entire relation between the basic state and the waves. This is what it's going to come down to in terms of the tropical dynamics. Okay, so the turning latitude written this way then, Re defined in this expression represents latitudinal e-folding distance of a particular mode of the solution we are looking for. linearized shallow water equations. So this is a function of Doppler shifted frequency, zonal wave number, meridional mode. Well, there are multiple modes, 0, 1, 2, 3, and so on, which is related to the Hermite polynomial as a solution, basic state, and the depth. So there is an infinity of free solutions relative to these parameters. R defined in 334, that is the equation we saw here. Okay, this equation refers to the distance traveled by a gravity wave during an inertial period, as I said. For a forcing scale that is less than 2 pi r, the system will respond by generation of gravity waves, and the forcing will be radiated away rapidly without feeling rotational effect. But if the forcing is a large scale, greater than 2 pi r, then rotational effects become dominant over buoyancy effects, and rotational modes will be generated. So irrespective of the value of the equatorial Raspy radius, it is the R that determines whether or not rotational low frequency mode is generated. Okay, the full solution for the constant basic state looks like this for the zonal, meridional, and vertical. Vertical is written as a function of the geopotential, GH, remember. In case you don't have an intuitive sense, geopotential is just the amount of energy it takes to move a unit mass to some height, and it represents potential energy because it's held there by balance of gravity and buoyancy and other things, dynamics. And if you can change the center of mass, then you can release that potential energy into kinetic energy. That's what is the basic story there. So that's that complex looking thing with the solutions for U1n, U2n, Phi1n, Phi2n, and so on, written this way. Obviously, we're not going to go into the details of it because we'll basically develop a common sense about the physics involved. The dispersion relation then is related to the turning latitude in this way, or the basic state in that relation. That looks complicated, but actually once you understand the physics of how we come to it, it becomes clear. Shallow water assumption, beta plane assumption, linearization, wave solutions. Add basic states, look at the impact on Doppler shift in frequency and equatorial trapping. That's what we are essentially doing.